All right, on page 327, there's a couple theorems up at the top of the page that you need to get in your notes. So we have angle bisector theorem. And the angle bisector theorem states that if a point is on the bisector of an angle, then it is equidistant from the sides of the angle. If a point is on the bisector of an angle, then it is equal distance from the sides of the angle. So if you take an angle or you draw an angle and this angle that we have here, I'll call this B. Now an angle bisector, that's a ray or a segment that splits an angle in half. So we're going to try to eyeball this so that we bisect this angle. So maybe like here. And we're going to put a point on this. Well, it's not an angle bisector yet. It's not an angle bisector until we know that these two smaller angles are congruent to each other. Now, since those arc marks are in there, we've got three angles now. We've got angle A, B, C. We've got angle C, B, D. And we've got the big original angle ABD. So if ABC is congruent to CBD, then that makes BC is an angle bisector. And this theorem states that if BC is an angle bisector, any point that's on the angle bisector is equal distance from the sides of the original angle. Now, when you're measuring distance from the side, all right, we've got the side of this triangle the side of this angle AB. And we're trying to find the distance to point C. That distance has to be measured along a perpendicular. The distance from a point to a line is measured along a perpendicular segment to the line. The distance from point C to side BD also needs to be measured along a perpendicular. So what the theorem says is that this segment AC and segment DC are congruent to each other. If a point is on the bisector of an angle, all right, so we determined that because angle ABC was congruent to angle CBD, that ray BC was an angle bisector, if a point is on the bisector of an angle, then it is equal distance from the sides of the angle. See how that works? Very similar to yesterday's theorem. Yesterday's theorem stated that if a point was on the perpendicular bisector of a segment, that it was equal distance to the endpoints. This says if a point is on the bisector of an angle, then it's equal distance to the sides of the angle. Now, the converse of this angle bisector theorem is also true. And that's right below the theorem you just wrote. And let's get that in your notes as well. The converse of the theorem states that if a point in the interior of an angle is equal distance to the sides, then it is on the angle bisector. If a point is in the interior of an angle, if a point in the interior of an angle is equal distance to the sides, then it is on the angle bisector. All right, it's just the converse of the original theorem. So that would be a case like you've got this angle again. And then you have a point in the interior of this angle, point A. And you're told that the distance from A to B is the same as the distance from A to C. If AC is congruent to AB, that's a point in the interior of an angle, equal distance from the sides. Well, what the converse says is that this point is on the angle bisector. So if you connected this vertex up here, I'm going to call it D to B, or I'm sorry, D to A or D through A. DA is an angle bisector. And this angle, CDA, is congruent to angle ADB. All right, angle bisector theorem. So if you look at page 327, example 3C. All right, if you're given, let's say you're given this A to C as 3x plus 5. And A to B is 6x minus 7. And you need to find AB. Well, if you know these two segments are congruent, you can write an equation. 3x plus 5 is equal to 6x minus 7. And you're going to solve for x again, so subtract 3x from each side. So 5 is equal to 3x minus 7. Add 7 to each side. And 12 is equal to 3x. Divide both sides by 3. And 4 is equal to x. So if 4 is equal to x and we need AB, well, wouldn't AB be equal to 6 times 4 minus 7? And 6 times 4 is 24 minus 7 is 17. All right, so A to B is 17. So the two key concepts are if the distance or if a point is in the middle of an angle or in the interior of an angle and it's the same distance from both sides, then it's on the angle bisector and these two angles are congruent. If you have a big angle with a bisector or a big angle with a ray coming out of it, and these two angles are congruent to each other, then the ray is an angle bisector. And if the ray is an angle bisector, then any point on that ray is the same distance from the sides of the angle. Okay? So then yesterday, the progression was, we talked about perpendicular bisectors, then we talked about perpendicular bisectors in a triangle. So today we're talking about, or we've now talked about angle bisectors, and then we're going to talk about angle bisectors in a triangle. So look at the top of page 328. How many angles does a triangle have? 3. How many angle bisectors does a triangle have? 3. If a triangle has 3 angles, then a triangle is going to have 3 angle bisectors. We're going to say that the angle bisectors of a triangle are concurrent at the incenter. Which is equal distance to the sides of the triangle. Triangle has 3 angle bisectors. They are concurrent at the incenter, which is equal distance to the sides of the triangle. So looking at that incenter theorem on the top of page 328, Again, this drawing is a little bit difficult, so you may want to watch to understand the concept and then draw it into your notes, or don't draw it into your notes. I'm going to leave that up to you. But if you've got a triangle, ABC, and we're going to eyeball, roughly predict an angle bisector coming out of A, and we're going to take it to about, I'll take it to about here. And since it's an angle bisector, these two angles are congruent. And then if we go to point B, vertex B, and we bisect this angle, we're trying to come out of here with a segment that splits the angle in half, and it's going to intersect with this line we just drew, so maybe like here. So if we bisect angle B, then these two angles are congruent. Now, if the first two bisectors intersect at this point, well, then the third bisector, the bisector for angle C, has to go through that point as well. All right? So now you can just connect, I'm going to call it point D and C. And if you connect D and C, that's our third angle bisector. So these two angles are congruent to each other. D is the incenter. And equal distance from the sides of the triangle. So now remember, when you're measuring the distance from the side or from a segment to a point, it is along a perpendicular. So if we put a segment here from D to E, it's 90 degrees. And then we're going to put a segment from D to BC, or from D to, I'll put point F right here. From D to F, that's the distance from the incenter to the side, and this is 90 degrees. And then if I take EFG, point G, right here, the distance from D to G is going to be along a perpendicular. Those three segments that I just drew, ED, FD, GD, these are all congruent. They're all equal to each other. Since D is the point of concurrency of the angle bisectors, then it's called the incenter. The incenter is equal distance from the sides of the triangle. And when you're measuring the distance from the side of a triangle to a point, it has to be along a segment that's perpendicular to the side of the triangle. So let's look at some of these questions they give you on page 328. Find each measure if J is the incenter. All right, so we're going to find each measure in this triangle if D is the incenter. And let's go with this D to C here. Let's say D to C is 15. Here's what we get. We get a 12. And let's say you're asked to find let's go with DE. Now this brings back some stuff that we haven't gone over in a while, okay? Look what we got going on over here. We need D to E. This segment right here. But we don't know the other two distances. So if we need D to E, if we can find D to F or D to G, we would know D to E, right? Because they're all the same. So look what you're given in this triangle over here. This pink triangle. I'm going from D to F, here, and here. Everybody see that pink triangle, DFC? It's a right triangle, isn't it? Because if this angle's 90, then this angle's 90. And we know two sides of that right triangle. All right, so what we can say is that DF, we're going to use the Pythagorean theorem is what I'm getting at. We're going to say that DF squared plus 12 squared equals 15 squared. And we're going to find DF because we know DF is congruent to DE. So watch, if we subtract 12 squared from each side, then DF squared is equal to, this is a good calculator shortcut. In your calculator, you type 15x squared minus 12x squared and hit equals. You get 81. If DF squared is equal to 81, then we find the square root of both sides here. And our DF is equal to 81 sitting on my screen. I push the square root button, and DF is equal to 9. So if D to F is equal to 9, well then what's D to E equal to? Very good. DE is equal to 9. So when you're doing these in-center problems today, don't forget that all of these triangles, all right, all of these triangles that have the distance from the in-center to the side as a leg, those are all right triangles. This yellow triangle here, or this blue triangle, this is another right triangle. BF squared plus DF squared equals BD squared. Okay? In all of these triangles, all of these right triangles, in this case, right up here, what's another right triangle? Lots of right triangles in these pictures. In this case, the side opposite the right angle is the hypotenuse. So up here, AG squared plus DG squared is equal to AD squared. All right, so looks like you're going to be using some Pythagorean theorem today to find the distance from incenters to the sides of triangles. All right, so let me give you some practice to get started on. Page 329. Five through 7. And then on page 330, 21 through 30. And again, we got study guide tomorrow and quiz on Thursday. Study guide tomorrow, quiz on Thursday.